This is the second part of my video for Unit 9, and the first part was that I was looking at an introduction to waves and pulses. This part I'm going to focus on standing waves. I have a third part that's very short that talks about beats and the Doppler effect, but hopefully this won't be very long. Now, first off, I like to describe a standing wave as a wave that looks like it's standing still. Now, it only looks like that. It's just that you don't see it moving side to side. And this can be kind of confusing because there actually is a lot of motion going on in a standing wave. Basically what happens is a wave is moving through the medium and reflects. The reflected wave superpositions with the oncoming wave. And when this occurs, and under special circumstances, we get this nicely constructive and destructive interference going on with a nice set pattern, and it looks like we have established a standing wave. So I have a couple of short little digressions. One is an animation that shows you what a standing wave truly looks like. So now let's see if I can illustrate what a standing wave sounds like. I use these for my labs. I have a pipe with water in it, and inside my outer pipe I have a smaller pipe. So basically I have an air pipe, open on the top, closed on the bottom because of the reflection. And what the lab is the kids sound tuning forks. They raise or lower the pipe to try to find each harmonic, which I'll talk about in a second, and that is a standing wave. So let's see if we can hear it. Right there. That's what a standing wave sounds like. It just sounds louder, and in fact that's what the standing wave is a result of. So let me just introduce a few terms that we tend to come across when we're looking at standing waves a lot. One of them is resonate. And basically that's a condition when we have a formation of a standing wave. The wave is resonating. That's what we heard with my tuning fork. The standing wave, the sound wave from the tuning fork was resonating as it went down the pipe and bounced back. Harmonic, resonance condition, very similar to resonate. Mode. These are all terms that represent a specific standing wave. And we're going to take a look at what those are in just a minute. You can have different types of standing waves depending upon your frequency, the length of pipe, all sorts of things. Antinodes, which you probably saw that, and I mentioned those on that little short animation. The antinodes are the parts of the standing wave that are always moving. So basically the crest and the troughs. And then the other term is the nodes, which is that part of the standing wave that never moves. I define the harmonic based on the number of antinodes. Other teachers don't do that. And technically you're not supposed to, but I have just found that it's easier to count the number of antinodes and base the harmonics on that. There is one basic exception you got to be careful about, but my kids haven't had trouble to work that through. So there's different types of standing waves that can form. It all depends upon the medium and whether the medium is fixed at the boundary or whether it's not fixed, whether it's open. That gets back to some of the stuff on the reflection on the previous video that I talked about with Unit 9. So I'm going to begin by looking at the situation where the medium is fixed on both ends. The classical example is a guitar string. It's tied down, it can't move. And so when it's fixed on both ends, what that tells us is we have nodes at the ends. So let's say we have a string, and we establish a standing wave in it. In the small, and it's fixed, so on my ends here I'm not going to move. But the smallest standing wave that can be developed, and you might have done this as a demonstration with a spring, looks something like this. I always draw both halves of the standing wave, because if you don't have a standing wave, you just have a wave. And so that's really important. You don't have to dot it. I just do. So here's my node, here's my node, here's my antinode. I have one antinode. This is my first harmonic. So if we take a look at it, if the length of my string is L, what I see is L is half a wavelength. And so I want my kids to understand and be able to identify how much of a wave do we have, what is the wavelength. The frequency that causes the first harmonic has a special name, and that's called the fundamental frequency, which I might have mentioned that, and if I didn't, my bad. The fundamental frequency is the lowest frequency that causes a standing wave. And so from there on out, as frequency increases, the wavelength is going to decrease since this is my lowest frequency. If I increase the frequency a little bit, the wave is going to shorten up, and the next standing wave condition I get when it's fixed at both ends is a wave that looks something like that. Not bad. I've got my nodes at the end, and I'm going to draw in my reflected wave, and so I have antinode, antinode. So this is my second harmonic. And you can see that now my wavelength is the same length as my string. As frequency goes up, the wavelength goes down. If I increase the frequency a little more, the wavelength is going to shrink down until I get to my next harmonic, which has 3 antinodes, and so it's going to look something like, hey, that's not bad. Antinode, antinode, antinode. You don't get point deductions for ugliness as long as you clearly show the antinodes. So this is my third harmonic for this situation. Now, one thing to keep in mind, the difference between my first harmonic and second harmonic basically is in this space I've shoved in another half wavelength. The difference between my second and third, I squished it down, I shoved in another half wavelength. That's the difference. Half a wavelength is the difference between each consecutive harmonic. And so that helps kids recognize. In all cases, this diagram is not necessarily applicable for all cases, but what is that the difference between 2 consecutive harmonics is half a wavelength. Now let's take a look at the situation where our medium is not fixed, but free to move at the boundary conditions. And so it's free on both ends. Free both ends. So when it was fixed, we have nodes. Now we have antinodes at both ends. So this is typically the case with a sound pipe. When it's fixed at both ends, it's typically the case with a string, but so this is going to be a sound pipe. So I'm just going to draw it like an open pipe. And so if we have an antinode at both ends, the smallest standing wave we can get is going to look like this. This is a little bit weird because I don't have a full crest here. I actually have half an antinode, and I have a half an antinode here. But if you add them up, that adds up to 1. And so this is my first harmonic. This is why I always look at antinodes. Technically, it's just easier, instead of trying to count the number of nodes under these conditions or antinodes, I just tell my kids, count the number of antinodes. If I have a half, if I have 2 1/2, that's a whole. Again, if my length of the pipe is L, what I have is half a wavelength. Very similar to when it's fixed. Let's do the second harmonic, which of course has 2 antinodes, and we have to have antinodes on the end, therefore we're going to have 1 in the middle. So a second harmonic is going to look something like that, with my reflected wave looking like that. And so here's half an antinode, a full half an antinode. Second harmonic. As it was before, the difference between these two, half a wavelength. I put in a full wavelength, and my length of the pipe is the full wave. So, sketch out the third harmonic. These take a little bit of practice to do. That actually didn't look too bad. Doesn't look too bad. Again, 1/2 lambda is the difference. Sketching these standing waves takes a little bit of practice. Got one more situation that we're going to take a look at, which is a combination of the two. This last situation is a combination of the first two, and so it's going to be the fixed free, meaning on one end the medium is fixed, on the other end the medium is free. That was the example with my pipe where I pulled it up out of the water, my open end and my closed end. And so what we're going to, and so some people refer to this as closed, open, fixed, free, means the same thing. On the side that we're closed or fixed, we're going to have a node. On the side that's open or free, we're going to have an antinode. This is a little bit different because in the previous two examples, our first harmonic, the wave was half a wavelength. This is going to be a little different, and so here's my pipe, and it's closed on one end. I'm going to have a node here, I have an antinode here, and the shortest wave that can reflect upon itself looks like this, which isn't that good. And if that's the length L, what we actually see is 1/4 of a wavelength. Previously, it was 1/2 of the wavelength. The other thing that's weird is we have half an antinode here. We don't have the other half like we did on the other side that was open on both sides. So because this is weird, and this is what I tell my classes, it's weird, so our wavelength's a little bit different. It's weird because we can't have half an antinode, so we're going to multiply by 2, and we get 1, which we call our first harmonic. There are all sorts of rules, again, to try to do this. I have just found it easier to focus on the antinodes. There's also all sorts of equations to get the frequency associated with this, whether it's open and closed. I don't do those. I want them to be able to sketch it and go, I have 1/4 of a wavelength, and from that figure it out. So let's do the next harmonic. Notice what I just said. I said the next harmonic. Our difference is I put in another half a wavelength. This is always going to be true. And so now what we have is 3/4 of a wavelength. I've got an antinode here. I have half an antinode here. I have a total of 1.5 antinodes. I'm going to multiply by 2. This is the third harmonic. I did not say draw the second harmonic. I said draw the next harmonic. Weird situation. We only have odd harmonics when it's open-closed. So this open-closed configuration has a lot of different things, and so that I've actually found that helps the kids keep it straight and help to keep it understanding how to do these particular problems. So now I'm going to sketch the fifth harmonic. So I just want to double check. I should see 2.5 antinodes to have my fifth harmonic, because I'm going to multiply by 2. And again, 1/2 lambda is my difference on what I've been able to put into that configuration. In all these cases, I'm keeping the length of my pipe the same. And so, because the wavelength is decreasing, my frequency has to increase. So keep in mind that when the medium is closed or fixed, we have a node. If it's open or free, we have an antinode. Now, when we're dealing with the medium of a string, that's pretty straightforward. That it's going to be fixed on probably both ends. When we're dealing with a sound pipe, that's a little bit different, because when we're dealing with a sound wave, it can be graphed either as a displacement or a pressure. And here's where you have to be careful, because they are literally the opposite. They still follow this rule up here, but you have to understand which one you're looking at. If they specify this is a pressure wave or this is a displacement wave, and they are just the opposite. So I think what I'm going to do is I'm just going to look at one that's open-closed, and I'm just going to sketch in the first harmonic. And I'm going to do it both ways. I'm going to sketch in the first harmonic based on displacement, and I'm going to sketch in the first harmonic based on pressure. So let's do displacement first. Here, if the molecule is right here, it cannot move. And so since it can't move, this is a fixed, or this is closed with respect to the displacement. And so for displacement, we have a node right here. Now, the molecules here at the open end can move in and out. And so we have a big old antinode here. And so our wave looks like this for displacement. Particles can move in and out, antinode. Particles can't move, that's a node. So it kind of makes sense here, closed, fixed. That kind of makes sense. Another way, though, that we can look at it is we can look at it from the sense of pressure. And what we're looking at is how does the pressure from the sound wave compare to the room pressure? And at the open end, there is no difference between the sound wave pressure and the room air pressure. And since there's no difference, that's actually a node. So I seem to contradict this a little bit, but this is the relationship between pressure and displacement. Here at the closed end, I can have high pressure compared to the room. And so this is an antinode for the pressure. So if I drew a pressure wave, it's going to look something like this. Pressure. Now, it doesn't matter which one you draw, unless the directions are draw the displacement or draw the pressure. I tell my kids, focus on one, understand one really well, and maybe displacement, since it follows these rules, is a little bit easier to follow. Then, if you like displacement, then just recognize that pressure is the opposite, where I have nodes for displacement, antinodes, which makes sense. If I have a lot of pressure here, that pressure is in that air, and that air molecule cannot move back and forth, so we have a node. Here, where I have a lot of motion for displacement, that's because there's no pressure keeping it still. And so it's important to recognize which one you're dealing with, and it's important to be able to talk about both and to discuss both. Understand one, recognize that the other is the opposite. Alright, the last thing I want to just kind of mention in regards to standing waves, and I apologize for this taking so long, but I really did cut it down a lot and only hit the basics and did not go over a bunch of any examples or anything, is one, you have to understand the scenario as to what's going on. And there's a lot that can happen with these problems and a lot of little changes that they can make. So, for example, there's always going to be a constant. And so let's say the constant is the velocity. Then there's going to be something that's changing. So let's say our frequency is changing, and then what they have to be able to predict is the wavelength. And so in this case, if velocity is constant and frequency goes up, wavelength's going to go down. And vice versa. If we're changing the wavelength, then we have to take a look at the frequency. If wavelength goes up, frequency goes down, and vice versa. We see this a lot in sound pipes. The air typically doesn't change velocity because the air temperature doesn't change, but we're looking at different wavelengths, different frequencies, that type of thing. We could keep the wavelength constant, and maybe we're going to change the velocity, in which case we need to look at the frequency. So maybe the velocity is going to increase, which means if velocity increases, the frequency also has to increase. Through this entire time, I'm thinking about our wave equation, some form of it. And usually here I'd be solving for velocity or frequency is velocity over lambda. And if that's increasing, my frequency has to be increasing. Or we might have the wavelength being held constant, and we're changing our frequency. What had to happen to our velocity? This is an example where we're fixed at both ends, a guitar string. They're tightening the guitar string, which is going to change the velocity. Something along those lines. Final situation, of course, is we're keeping our frequency the same. We're using the same tuning fork. And we're looking at how is velocity, and if we're changing our wavelength, if we're controlling the length of our wave, how's that affecting our velocity? And of course, the other situation is just switching these two around. So here again, I would rewrite the equation for what we're trying to predict. This is a case where our string is attached to an oscillator, and our frequency is maintained. So here's a demonstration that I do in class. An elastic string is attached to an aquarium pump. The diaphragm is vibrating at 60 Hertz, so that frequency is set. And by adjusting different tensions in the string, I can get different standing waves. There was a second harmonic that you just saw. Here's a third harmonic by loosening up just a little bit. And I think I show 4 harmonics here in just a second. It's a great way to kind of show the kids an example of standing waves. And it's a cheap thing to build if you wanted to build one. So that demonstration is really great to help illustrate to the kids and help them actually see standing waves, different harmonics, just by tightening or loosening the medium, and how that affects the motion of the standing wave. There's a lot with this wave unit, and it's really kind of strange because it almost seems like the AP says, oh, it's not that important, but there's always been one of the FRQs has always been a wave or a pulse type question, and since there's a lot of different types of questions they can ask, there's a lot of information to cover. I still have one more small part about waves. I'm not going to cover it right now. I'm going to cover it later, talking about beats and Doppler. But so far, I hope this has been some help. Thanks.